Hello everyone, good afternoon. Hope everyone's still okay. So this is the after lunch hour and everyone probably a bit full after lunch. Okay, so today's session is more we are talking about packaging design. So of course, as the title mentioned, as you've seen on the invitations event page as well. So it's more towards packaging solutions and in designs, okay, with other solutions. So obviously it's going to use Inventor and some other softwares. And then at the end of the sessions, almost at the end, so I'll be sharing about Flap Sims where it will helps to simulate the process of um, transporting and also sorting out the packaging. Okay, so let's see next. Okay, a bit of agenda. So basically, I can say half of the session is more towards some designs. Okay, and then the end we will be going towards some documentation and also process simulations. Okay, so my name is Said, so I'm your presenter for today. So let's just go towards the actions. So usually in this industry, so production processes, so you start with these four pillars or four main things. Okay, so probably companies, yeah, different company have a little bit a difference of arrangements, but in general, so this is it. So corrugating, converting, palletizing, and also warehousing and delivery. So we will try to address. We in this session we are not addressing on the machines design for the packaging, but instead more towards the paperwork design. Okay, and then at the end is more on warehousing and delivery. Okay, so here is the uh, so-called the end goal, so the end products. Okay, more like carton boxes. Okay, this kind of thing. It looks very. The design part is not that difficult, but it's just how do we get more from what we have. So in this case, in our Autodesk product design and manufacturing collections, and also Autodesk Inventor. What we want to know. So usually I will ask customer or whoever I talk to about presentations or for this purpose, this packaging designs is more like what is your company trying to achieve? Okay, so what are the major risks or challenges? Okay, and then what is the process? Okay, so usually most of the company would say they were trying to achieve to get more profits. Okay, to be faster in the productions, design and productions. Okay, to achieve or to be early than the deadlines. Okay, and then some risks or challenges probably like their machines or their collaboration potions. Okay, and then probably process is not working, it's not working well or not efficient enough. Okay, so then we'll see how we can help. Okay, so the hero products for this presentation will belongs to Autodesk Inventor, where Inventor is the main or the professional grade design. So in Autodesk Design and Manufacturing Solutions. So roughly it can do basically 3D modelings. Okay, so a bit all the basics or like you're doing jigs, pictures and everything. So Inventor definitely can tackle that, no problem. So a bit more into specialized modeling tool, things like sheet metal, if you're doing welded frames, okay, if you're doing 2M pipes. So Inventor have all these built-in libraries to help you to excel in all this design. Okay, so design automation. So this is fairly, can say unique to Inventor. So because from your design, you can actually automate. Okay, automate your design. So let's say we're talking about very simple products here, right? So a box. So one box probably do not have many different designs. Probably differences is more towards on the stamping and the exterior, but I can say most of them are on the sizes. Okay, so you can just create one models and then one models you can control the sizes by using form. So you don't have to go in and change dimensions and um, okay, or the details directly into the design part. So you can just use form to change. Even your normal salesperson also can help to do this. Okay. And then one more good part is, so Inventor is very, very good in their interoperability. So any other softwares or any other formats that you have out there, so probably you have your customer sending out some file formats, you can open it up in Inventor and then you can work on it. Okay, and then you can also export to all this file format in case you need to. Okay. So we're talking about inventors. In this session, we'll be talking about inventors and then nesting, a little bit of nesting, okay? And then a bit on flexing. Okay, so in case you're wondering, so Inventor also comes with the design validation application or solutions where you can stress test all your products. Okay, so you can test to see where is the weak points or where is the critical area. So everything in PDMC or product design and manufacturing collection can do all the linear, non-linear, thermal, vibration, and also dynamic simulations. Okay, and also machining, a bit of machinings and a bit of nesting where you have assemblies and then your assemblies need to be cut into shapes, right? Okay, so for this purpose, so for packaging purpose, so we'll be using, so I'm going to show that we're going to use a sheet metal command to do this packaging or paperboard design. So basically it's the sheet metal tools, but we somehow rearrange or repurposing it to do more on paperboards design or product oriented. Okay. So in case that you're involved in factory flow and factory process, so this product design and manufacturing collections also have the capability to help you to improve your factory floor processes and planning. Okay, so in case that you want to improve or maybe you want to expand or maybe creating a new factory, so you can also look at factory design utilities and also flexing later on to improve or to optimize your factory design. Okay. So usually, so in this industry, so sometimes it's quite straightforward where we just receive drawings or design from customer, or probably this is all done in-house. Okay, so usually we as a designer or as an engineer we requested a sheet metal drawings, or sorry, a flat pattern drawings if there is. If not, any measurements of the products will do, and then we repurpose it and make our own so-called flat pattern. Okay, so we are going to use sheet metal flat pattern to generate a flat pattern for the boxes, so that we can later simulate on the cutting. Okay, so we can also reconfigure our Inventor sheet metal rules, okay, to address all the paperboards or the paper, or because every product sometimes they have different thickness, right? So all this can be reconfigured accordingly. Okay, define our parameter box. So parameter box is all every dimensions or every measurements that we put into the design or the sketch. We can repurpose it, we can reuse it. Okay, so that later on we can control on the sizing. Okay, and then we use flanges to create a box, a paper box. So repurposing flange for paper box purpose, verify clearance, generate the flat pattern, generate 2D drawings. Okay, and then we use nesting to create the cutting optimizations. Okay, we want to plan our nesting and also generate program if necessary. Or usually, most of our customers, so they like to, from nesting, they like to auto-generate a DXF and then send to the machine. And the machine will read the DXF and then straight away to do there's a cut and so on. Okay, so we can also generate DXF from the nesting simulation as well. Okay, so example, so we obviously will start with very simple very simple sketch or shapes. So you can see instead of having dimensions with figures. So my dimensions already been configured to use names. So like box length, box height, box width. This you can configure in the parameter. Okay, so that it becomes standard, and so you're not adding new dimension every time. So you can repurpose the so-called parameter. So let's say we wanted to have a face, right? So for a box, so it could be a side face or a bottom face. So depending on how you want to plan your design. Okay, so in this case, so when I create a flange, so I straight away apply my parameter, which is I name it as box height. Okay, so automatically box height will get the measurement that's been that has been shown on the screen. In this case, is 60. And then we can straight away apply what's the rule, method rule we want to use. Okay, so from here, so we can, just to confirm, so this is the rule that I set for cardboard. Okay, so you can control your own thickness. So this is very straightforward. Just from very simple sketch, we are creating something like this. Okay, and then we straight away just adding in all the flanges just to make it close, right? So like a proper paperboard. Okay, so again, I'm using my height or box length, and then of course in Inventors or because it's parametric, so you can always add what do you call it? You can always add formula if you want to. Okay, so in this case, I'm adding in the length minus some clearance. So I indicate the clearance that I want. Okay, or we can just type in the value if we want to. Okay, so when we are editing the features, so when we are editing the face, so we can just select either face, edge, points, depending on our requirement or depending on our designs. Okay, to see what kind of modification we need. Okay, and then when you're doing some bends, you need to indicate whether you're bending it from inside or from outside or from the middle. So all that can be specified from within the applications. Okay, so from the features dialog box, you can specify whatever you want to form it. Okay, so that's the basic shape. It doesn't look like much yet, but when we move on, so we can see that you can see there are some boxes, some edges that need to be more refined. So now I'm going to add a bit more closure. Okay, so I'm going to select all the edges, okay, just to make sure we have some closure. Okay, and then every box, okay, every paper box, we have some width or clearance. Okay, so in this case, I'm going to use my width and then specify some formula divided by 3. Okay, or whatever standards or measurement that you have, you can also key it in. Okay, so you can see this bend position. So this is at the moment it's showing inside, and then it doesn't look too good. So it doesn't look right. Okay, so probably we can check and see. You can play around with the bend position inside, outside. Okay, to get a better result. So in this case, let's say if I change it to outside, you can see that it's lifting up. So the bend is now outside from the face, because the calculations of the face is adjusted to go to use outside faces. All right. So graphically, you see that it's a little bit different. Okay. So from here, what we can do next is maybe we start to adjust or give a bit more details to the box. It's not complete yet. Okay, definitely you can see there's a lot of things missing. Okay, so probably at the next edge. So we need to add more flanges on the next edge. Okay, so what we are doing here, again, we're just going to use very simple command. So in this case, we're just using flange. Okay, adjust the length. You can see by default it's using outside or inside. You can see the differences. Okay, and then maybe I want to make it a bit go up. Okay, not on the same level as that face, but instead it's going outside or inside, depending on how I want it to be. So let's say I select that, and then probably I extrude some face first. Okay, just to make sure that I added some extra height to it, okay, to make sure it's aligned. So I can just use that face, okay, to make sure that my extrusion just now is on the same height as that face. Okay, so that I will have to manually measure and key in the values. All right, so same thing that I just repeat it at the bottom there. You get the same thing. So just extrude to the objects. Okay, offset some clearance if I need to. Okay. All right. So now we're going to do next is a bit more on to clean up. Okay. So to clean up the things, or still we are adding in some. Okay, we haven't add in. So again, we just repeat that. Okay, you can see now we are adding in a new flange. Okay, to make sure that we have a bit of proper closing. Okay, so from here, so the clearance is not looking good. So we need to add some clearance. Okay, so you can see when at the height box there, you can see it's red means something is wrong. Probably the formula is not right. So I'm giving you a bit more just to correct the formula just now. Okay, I'm using the existing parameter and add a little bit of formula. Okay, so again, you can double check the band positions. So what good is we can visually check if there's any clashes. Okay, so probably we should leave some tolerance 0.01, 0.001 in case we need to. Okay, so now it looks a bit like a proper box packaging. Okay, so from here, because we do it in 3D, so we can also add some decals if you want to. We can add some decals and we can also create a flat pattern from here. Okay, so because we are using sheet metals command, so we have the ability to create a flat pattern. So you can see it automatically create a flat pattern. Okay, so that we can automate how our machine later on need to cut all this flat pattern, right? So obviously you will have one very big raw material or a roll, usually a roll of material. So you need to cut this profile into that raw material, right? So you can later on simulate how many can you get from maybe X amount of length, or maybe 5 meter, how many amount of box can you get? So you can simulate all that. Okay. So since we use 3D and it's parametric, we can also check when you do some sections, you can see from the internet and we can see if there's any clashes or anything that we need to justify, or like probably you want to add one more layer of flange over there just to make sure that the box is stronger. Okay, so this is common now where we add some internal support. Okay, sometimes the box is used for very heavy things, so we need to give it a bit more support. So you can also do this. Okay, so from here, so the rest of the design, so let me just specify probably we want it full length or maybe a bit of offset, so we can also play with that. Okay, so that's on the basic design. So let's see if I can try to go and open here. So let me just stop a while and see if you are looking at the correct box. So let's see. I'm not sure if you can respond. Okay, but can you tell me what are you looking at on your screen now? So are we looking at a PowerPoint or are we looking at my Inventor? I mean, are they having access to chat? Oh, okay, they can respond. Okay, all right. So now we are looking at Inventor, right? So this is the end product. So we know that we use all the basic sketches, okay, from a box. We just specify this length. Okay, so all this parameter is easily created. So every time you create dimensions, it will ask you can rename it or you can purposely create a standard. and then give a proper naming. Okay, so like box width, box length, and so on. Okay, so since we're using sheet metal, there are a lot more names to be here. So basically, the user parameter I created is only this, and I apply it to all of the dimensions, measurements created in this process earlier. Okay, so let's say we just finish that. So one of the good things that we use Inventor is the design automations, where we can play around and control the sizes. So you also know we can change the size directly to the dimensions, or we can create like a form, okay, a form for us to play with. Example over here. So let's say this form here is created with Inventor iLogic. So let's say this is for the top opening. So maybe I want to make it close. So I can just change it. Okay, and then maybe another one also. So it's closed now. So what about the size? So because usually the so-called parameter or the variations that always happens to this kind of product is the sizing. So let's say for width, so instead of 300, probably 500 mm. So within just one click, one click to change the numbers, and then one enter, it's auto update. Okay, so what about height? So maybe give a bit more height. So it's updated as well on the spot. And length, maybe with this add a bit more length. So it's updated. So if this is updated in the 3D model, so if you use this model to create a 2D drawing, it will automatically update it as well. Okay. So just imagine how fast can you respond to maybe your customer requests that probably they have a little bit of maybe different sizes. Okay, so you can come back to them very quickly because you have this automation. And since we are also applying materials, right? So you will also get a materials update. Okay, so let's say if we change the size, so the material properties. So in this case, I'm just using the generic material. Okay, so the mass is 2.334. So if I make it bigger, so it definitely will change the mass as well. Okay, this material just now I'm just using samples. So if let's say you want to create or to assign a material, you can do so. Okay, so in case the standard one do not have what you need, okay, so as long as you have the informations of the material density, you can always create a new material. Okay, this will affect the weight as well. Okay, if you change the size, maybe make it 800, make it bigger. Okay, and then if we go to model just to see and check that it will also update. Okay, the mass. So I'm just showing that it's updating. Okay. So the so-called the drawing creation is pretty much straightforward. So when we have the 3D model, so we can specify the templates or the drawings standard that we want. So in this case, I'm just going to use ISO. Okay, I should have opened this up earlier, but it's okay. So I'm creating a view for this product straight away from my 3D models. So let's say, let me move this here. Okay, so from here, of course, obviously we have some sizes. So scale, maybe make some changes to the scale. Oops. And then let's say right side. Okay, so let me just okay first. This one I don't want. So let me just move this around. So when I have this, okay, maybe I want to create some section view, which is I can. Okay, I can create this first. Okay, you can see it's automatically a section. But the thing that I want to show here is the dimensions, where whenever we change the size, it will also affect the dimensions. Okay. All right. So next, let me just go back to my points. Okay, so from here, I'm just going to show nesting. Okay, so let's say I have something, I don't use the example just now. So let's say from an assembly or from a part. So I can straight away create nesting. Okay, so even from assembly, so it will give all the options because we have different thickness, right? Different material and different thickness. So Inventor nesting will create different lines or different section of material types. Okay, so it will differentiate it by material types and thickness. You can see it automatically create a nesting from that assembly. Okay, the assembly that I use, the box is just one part. But in case that we have more complex component, we can straight away generate nesting from there. And we can control the raw material size, okay, so that we can optimize the numbers of quantity before we create the laser cut program. Okay, so from here, in this example, we are creating a laser cut program. So we need to specify the so-called the stock solid, the stock locations, and then so what type of cutting we are going to use? Is it water jet? Is it laser cut? Okay, which phase they're going to be the reference. So this is all this kind of setting up that we need to specify. Okay, in this case, we use laser cut. What's the machine feed rate, the speed, and so on. And it will help to simulate as well. It will simulate the cutting for you. Okay, so in case you want to see more details, okay, more details on the cutting, so we can so do that. So now what I'm doing here, this is I'm just checking into my server. Okay, so from here, once it's done, so we can also generate a cutting from there. Okay, so that's more on designs. Okay, design, drawing automation, nesting, simulations. Okay, and then a bit of collaborations with Vogue. Okay, so if you have questions, since you have access to the chat box, you can respond to the chat box. Okay, so next I'm going to show you a little bit on FlexSim. So FlexSim is more on process simulations. Okay, so we call it DES or discrete event simulation, where we can simulate an event. Okay, it's a simulation for modeling and also analysis. So the three things that always happens on the production floor is the variability. Okay, because real world, even though we do design very nice, okay, very tuned, right? But in real world, there are many factors that can happen. Okay, there are some unpredictable things can happen, and also predictable things. Okay, with random events like blackouts or whatever. Okay, so interdependency is to accurately model a process. So we are no longer talk about modeling a box, but we talking about to model a process. Okay, from one station, let's say example from the lorry who bring in your raw material. How do you want to bring that raw material in from the lorry to the storage in your warehouse, example. Okay, and then time. So from one stage to another stage, what's the time taken? So let's say from the lorry to the storage space, how long will it take? How many person will it take to transfer? Probably maybe 1,000 piece of raw material, example. How many person will it take? How long will it take? What's the best route? What's the fastest route to take? More like ways that tell you the best route to take. Okay, so we're talking about a 2D factory layout. Okay, you have your factory layout. Okay, and then it's even better if you have a 3D factory layout. Okay, and also with FlexSim, you can simulate your factory. So not just like you see in the example here, it's not just all the robot arms, but basically everything. So every process in the factory. Okay, so I'll show some of the examples. Okay, so what is FlexSim? So FlexSim is to simulate the flow of any process. Like in manufacturing, let's say you want to do laser cut or CNC machines. Okay, the time taken to assemble a products. Okay, material handling, like in this case, we are more towards material handling. Okay, so why use FlexSim? This is just to prove the the new layout is, let's say, new layout is better than the existing one, or maybe a new factory, we can provide this layout with some reports and simulations. Optimize existing productions, maybe in real world, in your factory, one of the line is slower than the other. So this always happens. Why? Probably because you have different type of machines. Maybe the storage is further, the operator also different. There are a lot of case or different factors. Okay. So some of the industry challenges that can be solved with FlexSims. Okay, all the processes, variety of processes in productions. Okay. Lack of interaction between system and process, high cost to the inefficiency. Sometimes inefficiency will give you more costs. Okay, so in this case, I will just cover a little bit more on material handling. Okay. This example in this company here is they simulate a model, show that the numbers of pellet pickup will rise from 70 to 100 pellets per hour. Okay, an increase of 43%. So how do we get all this kind of study? We simulate. Okay, so 3D animation will simulate and visually confirm where is the congestion in the conveyor line. How do we address that congestion? Maybe add another line of conveyor, or maybe add an extra extra stuff there to help with all the congestion and so on. So let's see. Okay, importance of DES is showing give you 3D representations. Okay, it evaluate all your ideas before implementation or before any investment. Okay, you can also run what if simulations. Okay, first rule of thumb, you will run simulation based on your experience, something that you know will happen and potentially happen. Okay, and then, or maybe something that you experienced before that have happened previously. So what if, again, so what if simulation means you give some rules to it. So example, so what happens if the conveyor line got stuck, or probably there's a blackout, or probably you have less people to help move the material and so on. So what will happen? So you have no study, you have no idea what will happen. So you can run this what if simulation to see what happens, because at the end of the day, you need to achieve your production goal of the day, right? Okay. So discrete manufacturing example, test layout options, visualize flow, optimize, validate changes. For electronic manufacturing, more towards people, so you can understand staffing requirements, testing. For warehousing, so you can see all this warehouse. So this is all, let's say you only have a 2D layout. Okay, so you can use all these 3D model libraries. You can see all this conveyor, all this racking system, all this is from within FlexSim. Okay, you can use them, you can visualize and simulate the process. Okay, you can visualize in 3D, VR, or USD. Okay, if you have some AGV, so automated vehicle, okay, the vehicle or the sometimes the machines that move around in the factory. So this will, you can simulate them as well, not just people. And also you can simulate, of course, you can simulate people to optimize where is the best way to go from one station to another, maybe from rest area to the stations. Okay, so the libraries that available in FlexSims, all the types of conveyors, all the warehousing libraries are related to warehousing, racking, some sample racking systems, floor storage, pane, A+ navigations, AGV, GIS navigator. You can even plan your transport. Okay, from, let's say, from Port Klang to your warehouse. So how long? What's the best route to take? Okay, and people. Okay, so, and the steps to build a model is very straightforward. So create layout, import AutoCAD, define the flow by connecting the fixed resources, detail the model by adding processes information. Process information means, so every machine have its detail, how much a machine can produce within an hour, example, what's the machine MTTA, downtime, how long will it take to repair. So all this information you need to key in. That usually comes with the machine's catalog, so don't worry. You can run the model and look at the dashboard for the reports. Okay, so here is example. This one I will also a bit pass through. So 4 step to build a model, create layouts. So, example, this is how FlexSim looks like. Okay, so we can add a model background, so we can add in a file, so it can be a 2D image, or in this case, an AutoCAD file. So you set an AutoCAD file of the factory layout. This is very simple. Example. So from there, we just insert in all the libraries. So let's say source. In this case, the source of raw material, where is the queue? Okay, who is the processor? So the processor is the machine. In this case, is the machine. So we're putting in the machines. Okay, putting in all this processor in, and then let's see. You can see on the right hand side is more all the information about the processor or the machines. Okay, so now we can define the flow, how the material will flow from one station or one process to another. So let's say from source. So how the source will flow, it will go to queue, right? So from raw material, let's say it will go to queue or waiting area, for example. Okay, to make it simple to understand, waiting area. So from the source to waiting area, how long will it take to move to this? So we need to specify. And then from our waiting area or our queue to all the processor or the machines, how long will it take? And then from our processor or our machines to the sing. Sing one is like, let's say the finished goods, or maybe the next stage. Okay, so after we define the flow, so we give a bit more detail about the models. Okay, about this process model. So from here, so how do we know that our process here is good, whether it's good or not? Okay, we need to run a little bit of analysis to see. So like all this machine, we need to specify the details like the process time. So within 1 hour, how much can it process? So all this information need to be keyed in. Okay, if not, we cannot get an accurate or even acceptable model. Okay, after we detail the models, we just run the models and evaluate the result. Okay, so again, this is very simple model, but I hope you get the idea. So from here, after we define all the machines or the process informations, okay, so next we're going to run the simulations and see. Okay, you can see the dashboard, so you can see our dashboard, see whether anything happened or not. So what's the result? So after you run simulation, any simulation, obviously you want to see some result. So how is our default simulation looks like? So now let's see. So let's add processes. So let me fast forward a little bit. Okay, so fast forward a little bit. So display, so we can see processor 1, processor 2, their states. So the idle time. Okay, so we can run speed, we can simulate. You can simulate the speed. So let's say at the earlier stage, I did not set the limit. Okay, the limit of quantity. Okay, so you can see average stay time 278.108. Okay. And so let's say we change something. So maybe we just change or add some bottleneck or some goals per hour, how much you want, how much we need. Okay, so to see how the process looks like. Okay, so after we specify the process time, okay, we add and we specify and see, change the details, can see we get a different result. Okay, run this simulation, you can see now our processor runs almost almost optimized, 93%, 91, and 86. Probably at processor 3 we can fully utilize. Why is it different? Probably because the further it is from the raw material storage. Okay, so that's probably the cost of it. Okay, so now next, let's say we want to try what if simulation. So what happens if I add another machine, or what happens if I add another operator, or maybe change operating parameter or change the layout a little bit. So what will happen? So from here, we can see that, first of all, so let's say if I want to add, you can see on the left-hand side, I have task executor. So like operator, I can add operator. So maybe operator can help to speed up the process a little bit. Okay, so we add operator. We also need to give the operator the rules or the informations. Okay. Okay, so add, okay, and then we need to specify from our source, okay, and then to our operator. So next to, we can add the total raw material example. Maybe I put 1,000 over there. So we'll see 1,000 stack. Okay, so by rule of thumb, probably one waiting area for, or one waiting platform for every processor, probably the best method. But let's say you don't have the space. So how you do? So in this case, so this person will move from one machine to another. It means he carry manually to every stations. Now we can see how our processor 1, 2, 3, and our operator perform. Okay, like example, you can see the orange box, right? At the operator one means they are travel empty. Means it send the box from the staging to the machine, and then he comes back empty. Okay, it means he travel empty. It's not loaded. Okay, offset travel empty. This one is the differentiators or the difference time. Okay, so with that you see you get some idea. Oh, with 1% you get this kind of result. So what if I add 3 persons? So 1% for one machine. So will it improve further? Will it make it better? So you can run this kind of what if simulations to see how it performs. Okay. Or maybe like I said earlier, maybe the staging area or the waiting area, we have one for every station. So the operator he can move nearer to the machines, so you don't have to move or walk too far. Okay, so it will help with the bottleneck or the performance of that stations. Okay, and then let's say what if you add 1% for every station, so it will improve further. But you can run the analysis to see the result. Okay, so that is just some basic understanding of what can be simulated and related to this industry, which is material handling and so on. Okay, so usually the types of waiting we divided to three: customer, products, and machines. So because customer need to wait, products in warehouse and also a work in progress, machine low utilization. So like earlier you see some machine perform better, some machines are low performing or low utilization. So we can put more work to that machine. So we know it's low utilization, so we can give it more work, or we can adjust the process or the workflow to address the low utilizations. Okay. So wait time versus utilization. So here is an example of wait time versus utilizations. Okay, as you can see here in this video, so you can see that all the boxes move on the conveyor, right? So you can see at the back, you can see some conveyors, they are stopping. So that's the bottleneck. So maybe you can set how much is the maximum before it need to go. Okay, before the roller need to move. Okay, so let's say line 1, line 2, line 3, and so on. So what is the best interval time? Like this example, so the robot arm. So you can see the robot arm is moving and also moving the boxes to the platform or to the machines. So what happened if you we change the so-called robot arm rotations or robot arm intervals between every boxes? Okay, will it perform better or will it last longer? Okay, this is the kind of information that we want to see. Okay, so everything that I showed you earlier, so on the design part, is everything that's included in the orange box. Okay, FlexSim also supposed to be here, but I haven't add FlexSim into this yet. Okay, I will add them later. So under MES, and also yeah, it should be under MES here. So any questions so far? I think we're just nice on time. Okay, so I know this session is probably a bit short because we go a bit express. So this is a 1 hour session. So in case you want to see more, okay, in case you want to learn more or to hear more about the inventors or the AutoCADs or the FlexSim, you can drop us an email or you can respond to us. So we will engage you accordingly so we can probably get in touch and to understand further. Okay, so questions?